Hi! In this video, we will be starting our journey into the study of mathematical logic. And before we start other forms of logic, we have to first take care of the most basic case of logic known as propositional logic. So, yes, this might be a new word, but it basically means that it deals with just the propositions, meaning things that are true or false, and connectives and parentheses, which is known as the language of propositional logic. So you just have a bunch of propositions and symbols, and then some connectives, the 5 connectives, which is negation, conjunction, disjunction, conditional, and biconditional. And then with that, then you have the parentheses as well. So what does it mean to be a language? A language is just like a syntax and the grammar behind it. So it should only be regarded as symbols and nothing else. And the meanings will be discussed in the future. The negation symbol is known as a unarily connective, and the others are binary connectives. And the parentheses will be just used to eliminate possibility of ambiguity in the readings, as we can later prove that parentheses actually can be omitted because they come in pairs for it to be a well-formed formula, but we'll talk more about that later on. So now that you have the basic symbols as P, the propositions P1, P2, P3, so on, you can form expressions using them by combining different type of symbols. So you got the P1, you can just combine it to be like this. Anyway, it doesn't need to have any sense yet because we're not talking about meaning, but you can just write it in a string of symbols, and that will be what is known as a expression. But this expression makes sense because that's what we have studied before. But this expression makes complete nonsense because we know that the parentheses must come from with one end and one close. So we are only interested in the grammatically correct expression, and these expressions are now known as the well-formed formulas. So what are well-formed formulas? Well, well-formed formulas must satisfy a set of conditions. Firstly, we just say that all the propositional symbols are already well-formed, and then once you know P1, P2 are well-formed, then the only well-formed formulas you can form are this, and this. Meaning with the connectives in this specific way with the parentheses open and close. And nothing else will be considered a well-formed formula. So it is something like we'll later see because this looks something like induction, and we'll later see what's the principle of induction for formulas. In the definition, the English is the meta language, and the propositional logic language we are defining is the object language. So we are using English to help us define our logic. So by the definition over here, it is easy to understand, but the problem is somewhat ambiguous. So you can actually make this more rigorous by using a top-down or bottom-up approach for defining it. And what does it mean? It means that we can define a set X of expressions satisfying some property defined over here, in these properties as closed. Because if you have this and this as well-formed formulas, then when you do some expression, it is still a well-formed formula. So the well-formed formulas set is closed under these expressions. And so we can say that the set of well-formed formulas can be defined, and this is a top-down approach, can be defined as the smallest closed set containing all the propositional symbols. So you just take all the proposition symbols, and then you add in all the things that make it closed, and the set must be closed at the same time. Then this set of expression, you just take the intersection over all of it, and then you see that is actually how we define the well-formed formula. And with that definition of top-down, we can actually say that it is the smallest in a sense by arbitrary intersection. So while the top-down definition is useful in guiding us because it tells us what set we are looking at, it doesn't tell us how the formula will look like. So we need to use the bottom-up approach, and actually you can show these two approaches give you the same definition by showing their equivalence. The bottom one, of course, will be that you imagine that you are like inducting it. So you got P1, you got P2, you got P3 as all your base cases. And then you construct formula from the previous line that you have. So you construct the formulas based on the propositional symbols, and then these will all be considered the well-formed formula. So you can keep going on, and that will give you more and more well-formed formulas based on the previous step. So what we want to say precisely is that we can call a finite sequence of expression A0 to AN, where AN is the expression that you want, known as alpha. Either alpha I is so this expression, this finite sequence, this construction sequence must be either these terms are propositional symbols, or if they are not, then there exists an earlier term such that it is one of the following forms created by one of the following terms using the negation and the other binary connectives. And if this construction sequence exists for alpha, then we say alpha is a well-formed formula. And what is to note is that because of this definition, we actually can see that the construction sequence will not be unique. Because let's say this is like P1 and P2, but your P1 here, P2 here, P3, P4, it's actually the same as having an expression formula with just P not P1, and then alpha, which is P1 or P2. So you can see how it does not need to be unique, and can be infinitely many different type of sequences. And with this step-by-step approach, we actually can now transform it. It is possible to use it as an induction way of deriving properties. So the induction principle for formulas states that if P alpha is a property of the well-formed formulas, if we are able to show that the propositional symbols all hold, and if two well-formed formulas have the property, then any negation or any connective using them will also hold. Then this property holds for all the well-formed formulas alpha. So like earlier we said why we can disregard the ambiguity of the strictness of parentheses. Well, we can use this principle of induction of formulas to prove this lemma over here, which states that the number of left and right parentheses must always be the same, and there are more left and right parentheses in any proper segment of each well-formed formula. Therefore, a proper initial segment of a well-formed formula must not be a well-formed formula. So there's a lot of words to unpack, and the most important line in here is just the number of the parentheses is the same. So let's start with that first to prove. And so we shall prove it here. We just let the property of having the same number of left and right parentheses be P alpha, and we perform induction on P alpha. Well, since it's already defined that all propositional symbols are well-formed formulas, then of course just having all the propositional symbols will obviously hold, because there is no need for writing a propositional symbols. There's no need for parentheses. And so now suppose that P alpha and P beta hold, so the number of left and right parentheses hold for alpha and beta as well-formed formulas. Since you put a negation sign and a connective sign, you need to add the left and the right parentheses. The number of left and right parentheses will stay the same, because you add one here on the outer, you add one on the left and one on the right. When you put it in a formula, it will be like that, and then continuing outside and outside. So the left and right parentheses remain the same. Therefore, the property holds, and according to principle of induction, P alpha holds for any formula alpha. And because of this lemma, there is only one way to read a well-formed formula when you write the parentheses already. So this is the reason why we say that this is the unique readability theorem of the expression. And because of this, we can actually omit the outermost parenthesis because it won't cause any confusion, and the negation symbol applies to as little as possible, because there's no need for this. Because this whole thing, you can remove this parenthesis and it's like that, and this part will cancel out, so it's just like that. And for repeating connectives such as this, we will read it from right to left. So we put the parentheses here and then the parentheses outside. So that's just the basis or the basics of propositional logic, and we will dive more into it in the next video. I hope you understand from this video what is it about first. So this is just giving you the syntax. What can you form? The propositions itself, and the well-formed formulas. Talking about the meaning, we'll talk about the meaning in other videos. So I'll catch you again. See you. Bye.